Hello everybody. Today I'm going to teach you the basics of quantum mechanics and physics and quantum stuff. Uh, I'm gonna call this unit 1.1 Blackbody diagrams. Basically, you know how when you heat stuff up, like a pan. Actually, it's not very good with pans. Like when you heat up a metal, right? It glows and it changes colors. Like it goes from just regular gray to red and white and all that, right? Well, a black body diagram is a theoretical item that when you heat it up, the color changes with temperature, kind of. Yeah, it's like you heat stuff up and it glows, right? And then, when it's glowing because the particles, right? They're moving so fast that they're radiating infrared radiation, and eventually it gets concentrated enough, or the waves, infrared waves, get squeezed enough for us to see it. Basically, we can see the color, is what it's saying, and they glow because electrons get thermally, they get agitated thermally. Like you poke someone enough, they're gonna put hands with you. You heat up electrons enough, and it's gonna radiate. And yeah, and basically a black body is like a material that radiates corresponding to its temperature. So if it's 600 degrees or 601 degrees Celsius, it's going to be color baby blue, something like that. It's like a different color for each temperature, for every temperature that it's a solid. And it's it absorbs and reflects light from its surroundings. Kind of like a mirror, but not quite. It typically refers to only absorbing and not reflecting light, because to absorb and reflect light would be like having my shirt, right? The reason it's the color it is because the material absorbs only, or doesn't absorb, it reflects this color. And if you get a dark enough color, it's not even reflecting anymore, it's just absorbing all the colors. That's what it's referring to. Hence the name black body diagram. It's going to be completely black because black absorbs as much light as possible, right? Heating it would emit light. So the only possible way that anyone theorized this could be possible, redundancies anyways, was if you had a sphere, it's massive, and it's you paint everything the darkest black color you can think of or find, and then you shine a light inside, and the light will reflect on the inside and it'll heat up the sphere, but also it would, because it's all black, it would absorb the light as well, and therefore being the perfect black body diagram. However, this doesn't work too well once you get down to other stuff, but yeah. And then so right there is a hole, and it's a big sphere, and it's just a hole for the light to go in. A black body diagram would be hollow, it'd be black to absorb all possible light, and when you heat the hollow cavity, the hole would glow. So I was wrong. The outside didn't glow. It's the hole that glows. So like, you'd shine a light inside and it would glow the cavity. Or something like that. And so basically, they wanted to figure out like the ratio, or like a formula for the ratio of like how the temperature would change. Like, if like this is a formula, and if you plug in the number of the temperature here, this is how much like the wavelength. This is what the wavelength is going to be for the light that's radiating out of it, right? And there are three main formulas. There's Rayleigh-Jean's law, Wien's law, or Wien, I don't know how to say that, if it's German or if it's not, I don't know. And then there's Schrodinger's law, right? Wilhelm Wien was a physicist, and in 1889, so like way long ago, these people like, oh, what would be the formula for finding out the temperature? That'd be like, what would it be? And Wien was the first dude who made the law, or made his law, right? It's technically a formula, but it's a lot easier to call it laws. He used classical thermodynamics to create the formula. And so I guess you would need to know thermodynamics to understand quantum physics. I will take it in college when I get there. But I don't think you need it for this. Anyways, it was a formula that tried to like explain the spectrum of the Blackbody diagram, and this is the first. Last one was supposed to be the first, but this is the first edited video. I edited the last one. I just didn't put any images because I was too lazy. That's the best excuse I have. There's the formula. U of, I think that's lambda. No. Give me a sec, I'm trying to find the, okay. Epsilon of mu and t, mu being, or nu and u, my bad. Epsilon, or whatever the form, you're gonna see it, epsilon of nu, comma t, or capital T. Nu is the symbol in chemistry and physics typically used for wavelength. So like wavelength will be nu always. And it's just like the epsilon is referring to like, with like quadratics you have f of x, yeah. And T being temperature. So epsilon of nu and T equals A nu to the 5th power times Euler's constant to the negative beta times nu over T. And so basically, the first part, epsilon of nu of T, or epsilon nu and T, is basically the intensity distribution of this light spectrum, right? At wavelength or frequency? Frequency or wavelength? Give me a sec. At frequency. Okay. It's basically where nu is the frequency, T is the temperature. I was wrong earlier when I said it was wavelength. My bad. Okay. Nu is frequency, T is temperature, A is a constant measured in the experiment, so it's just any random number you measure in the experiment. I can't tell you what it is because I don't know what it is. I could look it up and do more research, but that's what you have to do. I can't just give you everything. That's lame. Where's the fun in that? And the spectrum is given by the function over there. And energy density of light emitted is the function epsilon of nu and temperature. Beta. Ooh, yes. In this formula, beta it's negative beta. Beta is another constant measure in the experiment, so I don't know what it is. You could do it yourself. It's 2 things you have to look up. And formula worked fine for like higher frequencies. Like, I don't know what a high frequency is, but like higher frequencies, it worked perfectly fine. It just only failed on the lower frequencies, right? It like messed up a bit. Too bad, so sad. But then Raleigh genes, whoever they are, or whoever that is, came up with the law right there. And they came up with it in 1900, apparently. And it's same thing, same function. Epsilon of nu and temperature equals 2 pi nu to the 4th power over the speed of light to the 3rd power. All that, right? Times k and t. K is Boltzmann's constant, a big number. And c is the speed of light, as you can see right there. And you know what pi is. Everyone knows what pi is. 3.141592, something like that. And basically, Boltzmann's constant, I'm gonna put it right there, or over here, somewhere on the green screen. It's gonna be so annoying to edit later. Boltzmann's constant is 1.3807 times 10 to the negative 23rd joules something else. I don't know, man. I wrote these notes down and I didn't do my actual research. I wrote them down. Well, I did my research. I wrote them down like so long ago. This is from like February. It's March now. It's almost April. So a long time ago. And basically this formula had the opposite problem that the first one did. This one worked fantastic for like low frequencies, fantastic. And it just doesn't work at all for like higher frequencies. It's like iffy, you know what I mean. Anyways, erase that. Okay, and then Max Planck, this guy, like Max Verstappen, but this guy is for physics. This guy is crazy. He does all sorts of stuff for like waves. Yeah, go research Max Planck. I messed up at the beginning of the video when I said it was Schrodinger. It might have been Schrodinger. But Schrodinger does have to do with this. This is quantum physics, yo. That's so corny. That's so corny. Okay. Max Planck. This goober, I'm gonna put a picture of him right there. This goober, he's the dude that invented quantum physics. He's the first to like think of it, to make, like, to write, do anything with it. He's the goober that's making me suffer and study and do all this for fun. Because this is not even for school, this is for fun. Okay, okay, Max Planck. He was off his rocker by what people thought was his rocker. He had the reason he was off his rocker, or people thought he was, is because he had a suggestion that was crazy, right? He thought energy waves can exchange with matter, or energy waves exchange with matter is discrete, and it's not continuous, right? Basically that means like the way energy interacts with matter is like a gradual change, right? It's not from here up here like a linear change, it's gradual, kind of exponential, but not really. He thought that the energy sorry, I'm blanking out here. Energy of light emitted came only in integer values. Now, people who code know what integers are, or if you're like in a certain grade, I think 7th grade maybe, I learned about integers. But basically, an integer is anything that is not negative. I think it can be negative. I can't remember. Anything that is not a decimal. It's like 1, 0, 2, 3,
4, 5, 6, but nothing in between. Nothing between 1 and 2. Sorry, 1 and 0 or anything. Right? Those are integers. So yeah, and you can't put this goofy little thing to signify, oh yeah, they can't be integer, they have to be integers. It's E equals NH, or anything new.
H is a universal constant, now known as Planck's constant. You use it in waves. You can see it in my waves video. Go check it out, please. It'd be really cool, you know, if you checked it out. It's H is it's Planck's constant now. It's 6.266 times 10 to the negative 34th power joules per second, joule seconds. And I don't know what that is. I don't know what I wrote down here, okay? My bad. Anyways, that's what H is. And this, guys, really cool formula right there. Super hard to write out, you know. If you're taking notes, my bad. I had to write it out 2 times because it's too hard to write. But basically, epsilon of nu and he equals 2 pi Planck's constant nu to the 5th over just that right there. Like that little thing, just that, over speed of light cubed times, and it's parentheses, Euler's constant, which is, or not Euler's constant, it's E, which is Euler's number, maybe? It's a weird number used in trig a lot. I don't know why they chose that number, but cool. Euler's number to the power of Planck's constant, so 6.266, or no, 6.626 times 10 to the negative 34th power. And this is all like, it's Euler's constant, or Euler's number, right? My bad. Euler's number to the power of h nu over kt. That's done with the exponents right there. Minus 1 and parentheses. Big number, right? It's crazy. I don't know how you come up with this. But basically, Max Planck, super cool dude. This formula works all the time. Doesn't matter when, doesn't matter who, what. It works all the time. And It's known as Planck's quantization rule. And this right here is the birth of quantum physics. And it's basically saying, that energy of all oscillators is quantized. And what that means is the basics of quantum physics lies on the idea of quantization, which is basically like measuring quantities in discrete, not continuous values. Or units, my bad, units. You can ask ChatGPT to dumb it down for you. I don't know how to. Basically, it's like measuring quantities is done in like discrete, non-linear, non-continuous units, right? Like it gradually changes or something. I don't know. It's like not continuous. It's not linear. Probably. But yeah. KT, I gotta figure out what that is. Hang on. Okay, so basically, K is a wave vector, whatever that means. Basically, this part of the video is going to be put back to the beginning, because I'm not leaving this out to the end. Yeah, no, I'm not. Oh no, K is kinetic energy. Okay, I'm not putting this at the end. I'm moving it over. So, basically, hello everyone. I'm Matthew, and I'll see you next time.